away. Let's, yeah. Woo! Okay, refocus now with all this sugar in us. So, we have parametric and polar in this chapter. Actually, before we begin, I want you to raise your hand nice and high. Yep. Bring it back. Pat yourself. Say, I made it through series. I survived series. And then give yourself a little hug. And say, series is over. You did it. Okay. So you have survived series. You may not have thrived, but you survived. Just kidding. Most of you guys did great. Okay. So now we're in something completely different. And I know you're kind of like, oh, finally, okay? It is much easier than series. However, don't let it slip. You're still going to have to memorize a lot of formulas. It's still Calc 2, but in my opinion, it is much easier than series, which makes it a little less fun, but okay. So, parametric is what we're going to start with today. Yes? Not at this moment. Okay, we're going to start with parametric. We can go back to series. You want to go back to series? Okay. We will, but not at this moment. And if you recall in calculus, we don't get to a lot of the real-life applications. This is more of all of the math and the theory behind other disciplines' real-life applications. Okay? So when you're like, this is more of a pure math, which means you're just doing the math. Okay? Okay. So what is a parametric equation? Parametric equations are now going to involve 3 variables. So you have an x, a y, and then you have a parameter. So that parameter is often the t. So for our equations, we will often see the t. You could see it as theta. You could see it as any parameter. T is just the most common one to use. So now you're going to have 2 equations. You're going to have this x of t, and you're going to have this y of t. These 2 put together create one graph. The big thing of parametric is that you're going to have what's called the orientation, or the direction, the flow, and you need to use arrows to show the direction. So if you graph any parametric equation, if you graph any polar equation, we get to that as well, you're going to be showing the orientation. So this is new. Back when we just had rectangular, that's what you have been doing, x, like y equals x, okay? You didn't have to do the orientation. With the parameter, you do. So let's see if we can understand this now. I want to sketch this guy. Before I start sketching it, I want to think through a little bit more. So let's first look at this TX graph. So this one right here. Okay? How would I graph the square root of t? At 0, I am at 0. At 1, I'm at 1. And it continues up, right? Okay. Let's go to the other graph here, this y equals 3 minus t. So now I have t and y. And this graph is 3 minus t. So I know I'm up here at 3, and then I have this slope going down. So it looks like this. Everybody agree? Okay. Here is where the trickiness begins.
Mr. Rose?
Yes?
Hi, I need Chris Sweat to stop by attendance during passing time, please.
Okay.
Thank you.
Okay. So when I talk about domain, I am talking about x's. And we always think we have x, y, yes? But now in parametric, t is always the parameter. So my domain is right here. And over here, I am finding my range. So right here, what is my domain? What is x? X is, yeah, so it's right up here, greater than or equal to 0. And here, as I look at my range, this range goes everywhere, right? So my range is, yeah, y is all real numbers. So that's different, because we're always used to looking at the horizontal axis. But now that domain is the x, and it's on a vertical axis. Okay, so as I go, what restrictions of t do I have? Do I have any restrictions of t? Okay, so I know t has to be greater than or equal to 0 as well. Agreed? So as I go plug in t to x, what value do I get out? 0. When I plug it into y, I get out 3. This is our point. So this is now rectangular because I have my x and my y. So we're back to rectangular as we plot. And I'm going to go 0, 3. And when I plot that, I'm going to say that that is when my t was 0. Anytime you're in parametric and polar, you guys, it's so beneficial if you plot that parameter, like stating where you're at. Okay? Do the next point. 1, 2. So now at 1, 2, and that's when t was 1. Do the next point. Radical 2, 1. Radical 2 is approximately 1.4142. So 1.4142, 1. Square root of 3 is 0, and 4 is 2, negative 1. So square root of 3, 0, and 2, negative 1. Okay, so I can see how the particle is moving. It started here, and it moved that way, that way, that way, that way, and it's actually continuing on. Agreed? So I'm going to show my arrows of direction. I do. Because this is the thing. Sometimes you may have 2 endpoints, and then the particle may travel this way, and then it starts to travel this way. And then it bounces back, and then it bounces back. And it goes just doop, 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 forever and ever and ever. Okay? So, yeah, parametrics are a little bit different. So let's go look at our calculator. And we're going to go to the mode. And in your mode, first off, everybody's always on radians. Okay? The function is that rectangular that I talk about. That's what you're always in. We're going to go over and hit parametric and hit enter to save it. Okay? So now you're in parametric. Now when you hit this button, the default is T, not X. That one right there. Okay? Go to your Y equals. Now you have, see, like, you have 2 things needed for 1. Because that's the set of parameters that go together. So in the X, you're going to put the square root of T. And in the Y, you're going to put 3 minus T. Then just hold up for me until everybody gets that. now, raise your hand if you need more time to write that. Go to your window. Now you can start your t-value where you want, and you can end your t-value where you want. I said, hey, what if I started at -5? Well, is it going to show anything to -5, -4? It's not going to show anything until what? 0. So I don't care. I can start at -5. Doesn't matter. Then I said, oh, I'm going to end my t at 10. Does that mean that the graph is stopped moving? No. So could I actually go to 100? Yeah, I could go out for a very long time. What's going to happen as I put in a bigger and bigger number? It's going to take it longer. The t step is saying, if my t was 0.001, I'm starting at 0, and then graphing 0.001, and then graphing 0.002, and then graphing 0.003, which would take forever. Okay, you know what movie that's from? Forever. Huh? Okay. So anyway, it would take it way too long. So leave the t step where it is. That one is usually, and if you make it too big, it's going to look all jagged, right? Because like if you go from 1 to 5, it's just going to draw that straight line, and it's not going to look smooth. Okay, and then I just left my window the same, 10 by 10. So when I graph, I put 100, didn't I? So it kept going. If you had 10, it actually stopped. Okay, but that doesn't mean it actually stops. That's just what you told it to do. Okay. So that's the parametric. And did you see the direction it moved? The same way that we just talked about. Okay. Okay. So eliminating the parameter, to change from a parametric equation to rectangular equations, the first thing we're going to do is solve for t in the easiest equation. So looking at this one, it wants me to eliminate this parameter and go back to rectangular. Which one is the easiest equation to solve for t for? Okay, let's see. Solve for t. What is t equal? No, it doesn't. Oh, is that really so easy? No. I would not choose that. I'm going to have 2 equations again to try to manipulate, okay? So which one do you think I should start with? Okay, so x equals the ln of 2t. Go solve for t. Everybody good? Then it says, then substitute into the other equation. So now we're on step 2. So we're going to take the other equation and substitute in our t. And if you want to simplify, great. Hey. All right. So this is the thing, though, and this is what gets tricky. This is our what equation? This one right here is the, what's this called? Rectangular. So this is my rectangular. This over here, these were my parametric. Will the graphs be the same?
No.
Sometimes. Not always. So they are the same on a given domain. Okay? Okay? The domains can be different. So first off, parametrics, these guys show direction. These guys don't. There's no like real start. Okay, there's no parameter. But the domains can be different. So let's go have a little battle here and see what happens. Okay, it's a duel. Time to duel. Get ready to rumble. So, on this one, let's look at this x equals the ln of 2t. Again, let's see, an ln graph, the 2t doesn't really shift it left, right, up, down. It's just the growth, but still going to not change the domain range, right? So it still looks like an ln graph. And this was t, and this was x. Yes? So what was my domain here? X is what? Yeah. Okay, so this is the domain part, right? So that's, again, the tricky. So here, this is all real numbers. Agreed? Okay, let's go graph our y equals t squared. So again, I have now t and y, which looks like this. Okay. So my range is y is what? Greater than or equal to 0. So that's where I got my range. There's my range. There's my domain. Okay. Now let's come over here to my rectangular. What's going to happen here? So let's graph this, and now we are in xy. Yeah? So as I go to graph, it's still an E graph. There's no up, down, left, right transformations. So what's my domain here? All real numbers. And what's my range here? Greater than 0. Sorry, in this case, am I a little bit off? Okay, what I could put, yeah. And sometimes in parametric, it could be the whole line, and then over in, or sorry, not in parametric, in rectangular, it could be the whole line, and then in parametric, it only hits that part of it. Okay, so just pay attention to domain and ranges is what I'm saying when you're going back and forth. That's what can be different. Okay, so this is not AP, but it's a lot of fun just to see. It preps you for your college. So, yeah. So, general parametric curves for conics. I know conics are always the favorite. So, you have an ellipse set up in parametric looks like this. An ellipse setup and rectangular looks like this. They're both ellipses. Okay. A parabola and parametric looks like this. Parabola looks like this. And rectangular. Okay. A hyperbola looks like this or like this, depending on if it opens. So this is east-west, this is north rectangular. Yes, this is always a minus for hyperbolas. When it's a plus, it's an ellipse. So I apologize for that typo. Okay, so that's like all math analysis stuff that you do. We're gonna look and we're gonna sketch this curve. We're gonna sketch it using what we know from first. I'm gonna do a little battle again. So first from parametric, then we're gonna look at the rectangular. Another battle, boy. Okay. So parametric. I'm going to set this up a little bit to match that A and the H and the B and the K. So in front of secant is just a 1. And added on to secant would be a 0. Same thing, right? With my Y, I'm going to do the same thing. Like this. Okay, and why am I doing this? Because this value right here is my A. This value right here is my B. This value right here is my H. And this value right here is my K. H goes with X's. Okay, yeah. Okay. So this tells me that I am centered where? 0, 0. That's my HK. So that's the first thing I'm going to go do. Huh?
Are the zeros added to the betas, or are they added?
Just the whole equation. Otherwise, there would have to be parentheses. Okay? So I'm going to have this guy going on. So I know that I'm centered right here. Actually, I'm going to use yellow for that. Because that's not on the graph. Okay. So I know I'm centered at 0. My A and my B is telling me how far I'm coming out from my center. So the square root of the 1 on the x's goes out to 1 and 1. The square root of 1 on the y goes up to 1 and negative 1. And then you should have been taught this way in math analysis. If not, I'm sorry for you. But you're going to now make a box. Okay? It's most easy way. Then you're going to do your asymptotes. They have to go through your center and the edges of your box. Okay? And then I know that secant is with the x, so this is opening, nope, east-west. So then I can follow, and it looks like this. So there's my graph. Okay, so that's a review for math analysis of the whole graphing part, but now with parametric. Yes. So it tells me, I know that if secant's with x, it's east-west. Okay, rectangular. Whenever I'm converting these secants, tans, or sines, cosines to rectangular, you're going to be thinking the Pythagorean trig identities. Okay? As you go to convert those guys. So which Pythagorean trig identity am I going to use with secants and tans? Secant squared theta. Nope. I could say -1 or equals however you want to get it, as long as it's the same. Okay? Okay, well what is secant squared from what we had? We know that that's just going to be x squared. Does that make sense? Equals, what's my tan squared? Y squared, and then plus 1. That just drops down. So this equation is x squared minus y squared equals 1. So we could again think of it as like over 1 over 1. So here my a squared is 1, so a is 1. My b squared is 1, so b is 1. I am not subtracting anything, so my h is 0. And again, I'm not subtracting anything, so my k is 0. And will I get to the same graph? Yes. And again, how do I know I open on the x's? Because x comes first. Okay. I am only going to do this parametric. I'm going to convert it to rectangular and then graph it. So what equation will I need? Cosine squared, and in this case it's a t plus sine squared t equals 1. But Grant, I don't have a cosine t, I have a 2 cosine t. Oh, I could do what first? Divide the 2 over. Oh, so cosine t is actually just what? X over 2. And sine t is actually just y over 3. Now, can you keep going? So that would be x squared over 2 squared plus y squared over 3 squared equals 1. What's the problem? Why? Oh, okay. Peyton, can you keep it put away? Thank you. Alright, so... Ooh, that was bad. So now let's see, where am I centered? Where am I centered? 0, 0, right? I don't have anything minused. So I'm centered at 0, 0. How far out from the center do I go on the axis? 2. Because it's a squared, right? So the a is 2. How far out from the center do I go on the y's? And since it's a plus, this guy is an ellipse, which I can see. It's like a football. Oh, football. Oh, I know. But I do not play football. Okay, so that's the little extra fun. Even though it's not AP, this is good to know with the conics and how they're related to parametric. Okay, so if I asked you to find a set of parametric equations, there are infinitely many ways. You can do this in so many ways. Okay, can you get your water? Okay, so there are infinitely many ways that you can do this. So I could say, hey, if I let x equal t, y would equal 2 over t minus 1. There's one way. Okay. What if I let x equal t squared? We'll do that one next. I like that one. That's my favorite, actually. Okay. Then what's y going to equal here? Yeah. Okay. Let's say I let x equal t plus 1. Y equals 2 over t. Again, could I do this in infinitely many ways? What's the only thing, though, that could be different? The domain and range. Okay? So we could find these, just make a little note, domain and range can be different. What else can be different? Well, it'd be part of the graph at least. It could be restricted on some domain and range, but what else could be different is the arrows, the orientation, the flow. Okay? I can't spell. Orientation. Arrows. Could also be different. For all of these infinitely many.
Shouldn't x be t minus 1 the last one? Y is equal to 2 over t, shouldn't it?
No, if I plug in t plus 1 and then minus 1, yeah. Okay. So, movement. What causes the horizontal movement is x, and you're looking for the movement, so it's going to be the change of x with respect to time. So that's your x prime, or your dx dt, okay? Which is the same as dx dt. That causes you to go left and right. To go to the right, dx dt would be positive. To go to the left, dx dt would be negative. Now what causes this to go up and down? The y's. Okay, so if dy dt is going up, then it was positive, and if dy dt was going down, then dy dt was negative. Okay, so that's dy dt is the same as saying y prime of t, same thing. Now the slope overall is y prime over x prime of t, because that's like saying dy dt over dx dt. And hey, what does that cancel to? Dy over dx. The dt's cancel. Okay, so to get the slope, we can take the derivative of the y with respect to t over the derivative of the x with respect to t, and that can simplify with the derivative of the y with respect to x, dy dx. Okay, so this is what's cool about the parametric, is it's breaking it down into horizontal and vertical movement. We didn't get this before. We just had the slope. Okay, so let me ask you this part really quick. If my slope is positive, then what are my two types of movement? Let's say my slope is positive, and I am moving to the right. Then it has to also be moving up, because you can have a positive over a positive, right? Let's say my slope was negative, and my dx dt is positive. Then it has to be moving down, because the slope will be like this, right? So you could think like this, positive, positive, like this, positive, negative. Agreed? Let's say that my slope was positive, and I am moving to the left. Then I'm also moving down. Did I just do that in the right way? Yeah, positive would be negative over negative. Are you getting what I'm saying? I'm in reverse right here. So if I'm a negative, then I have to either be up and left or down and right, basically. So that's kind of nice to know too. And object moves in the xy plane so that its position at any time t is given by the parametric equations of these connects. What is the rate of change of y with respect to x when t is 3? So this is asking you to find what? The slope. So to find the slope, I have to do what? I have to take the derivative of y of 3 over the derivative of x of 3. And this would give me the slope at 3. So this would give me that dy dx evaluated when t is 3. Okay, go see if you can find this. Y prime of 3 would be 3 over the square root of 25. Am I going too fast? And x prime of 3, 27 minus 18. Okay, so see how you did. If you need help, I'm going to walk around. Okay. So this is my question for you. I know this is multiple choice, so the work isn't graded on the test. But I just want to make sure we understand. If I said dy dx equaled 1/15, am I correct? Okay. Dy dx definitely doesn't equal this numerical value. Dy dx, when I evaluate it at 3, equals that numerical value. So if you would have left this off, I would have given you a -1. You would have missed that point. That is a false statement. Dy dx equals that t over the square root of t squared plus 16 over 3t squared minus 16. Now what if I said that that equals 1/15? Again, -1. We don't have, what if I put it here? Am I still at an error? Yeah, because now I have a general equals a numerical equals a numerical. Now am I okay? Yes. Do you understand where I could count you off? Okay. So be careful in your notation that you don't have a false statement here. Okay, particle at rest is when both your x prime and your y prime are 0 at the exact same time. Then the particle is at rest. Okay, so basically if you had a slope of 0 over 0, which we know is indeterminate, okay, but that's telling me the particle is at rest. It's not moving anywhere. So this one wants to know, at which of the following points is the particle at rest? Okay. So I want to know, where's x prime of t equals 0 and y prime of t equals 0 at the same time? Where does that happen? That's where the particle is at rest. So can you go solve those equations? So what's my answer? Okay, so this occurs when t equals 2. So the particle is at rest at time 2. Because it's the only place where both of these are 0. But this didn't ask me the time. It says what's the point? So what do I do at the time now to find the point? Plug it back in to the derivatives?
No.
To the original. Okay, go do that now. So I got A. A. Are you okay with that? Right. This is an AP problem, and I want to see how you do. Go for it. I am going to give you 2 minutes. Starting now. Seconds in. So do you have to reduce? No. 1 minute. Very, very, very easy direct explanation. 30 seconds left. Okay, time. Let's see how we did. If I'm talking about horizontal movement, I'm talking about, yes, dx dt, right? So I'm going to say dx dt equals this. Is that right? No, what's wrong? Oh, did you see how I just missed that point? Why did I just miss this point? No, that's what I have! Why did I miss the point? It's on a technicality, Grant.
Dx over dt does not equal.
No, but it does when I evaluate it at 2. Okay. So it's moving to, oh, sorry, yes? If you said x what? Yes. So you could have said that this is x prime of 2. That's great. What if I said this?
No.
No, wrong. Point gone. Okay? Okay. That is fine. Okay, so this is moving to the, okay, to the right. Because what? No. Easy justification.
You not have to put x equals 2.
Okay. Hold on. I meant to say x prime of 2.
Minus 1. Minus 1.
Now, that's really, really easy, but you still didn't get the point. Because there's one little thing you have to say with it. No. Okay. And x prime, or sorry, y prime of 2 is not 0. Okay. Oh no, hold on. No, that's not. I'm thinking of something else. Oh, it's Friday. Okay. No, that's all you needed. I'm just testing you all. That's all. Okay. Okay. dy dx when t is 2. Well, we've already got the x part. What's the y part? Done. Now, this is actually a calculator problem, but are we going to take the time to put it into our calculator? No. Is this the correct answer? Yes. We are good. We are done. Peace out. Drop the mic. Okay? You've got full points now for this. Okay. It's the horizontal tangent, which we get to next time that you have to do that second part. I'm so sorry. I just kind of jumbled in my brain. No, I wish. I know. Okay. So the last thing that we're going to go over today, and this is a review, but this shows up on parametric all the time. This is the fundamental theorem of calculus. You remember this? We love this. Okay? It's our fundamental theorem of calculus. Okay. Okay. So this is the fundamental theorem of calculus. And we're going to use this in parametric equations. So a lot of times you're going to have this from some time to some time, and you'll have like an x prime of t dt, where you're going to have like that x of b minus x of a. So you could see it with the x's or the y's. So they're asking you to find another x value or another y value. This is how we're going to see it and how we're going to set it up. okay, with this fundamental theorem of calculus. So this one again, they gave me, it's the same problem we just saw, but now in part B, I think they only wanted the x coordinate, but we're going to do both. That's why I typed it up. Find the x and the y coordinate. Now this tells me at time 2, this is my position. So what is 1 actually equivalent to? X of 2. And what is 5 actually equivalent to? So that's what that point is telling me at time 2. So they're saying what's happening at time 4. So what's x of 4 and what's y of 4? That's what they're asking for parametric. So we're going to set up our fundamental theorem of calculus twice. We're going to do it for the x's, then we're going to do it for the y's. So I'm going to do the x's with you. So on my x's, what are the 2 times that I know? And we're, and 4. So I know the 2 and I want the 4, the 2 times that we're dealing with. And then my dx dt, you could write it in, or you could say dx dt. Okay, but if you like to write it in, you can. That's up to you. And now I know that that equals x of 4 minus x of 2. This part right here, we put in the calculator to get my answer. This part right here is what I want to know. And this part right here was given to be what? Okay, so that was 1. So let's go put the first part in the calculator and make sure we can get the same thing. So after I put it in the calculator and get my answer, I got 0.253, or you could have had 0.252 if you truncated. You may round or truncate. So it was 0.252 what? 9? Truncating means you just cut off 3 and you write what you have. So everything else, everything else past there goes away. Yes, on the AP test you can truncate or round your very final answer. Not until your very final. It's just that you can't. Okay. We can go over why in a little bit. Okay, so let's look at this. So now I said that was in the calculator and it gave me this answer. That's what I'm trying to find, and that was already given to me as well. So now it's an algebra 1 problem. What does x of 4 approximately equal? 1.253. So there's the x value when time is 4. Yep, or 1.252 if you truncate it. The very final answer, not to the very final, can you round or truncate to 3? Okay, I want you to find y of 4, and I'm going to put it up here and see if you get it correct. Grant, now that everybody else is on that. I truncated when I was allowed to on your grades. Anything like an 89.93, it's like an 89. And I just truncated off and only allowed that to the C. But now in Infinite Campus, which is so much better than all of the mining and complaining, because you couldn't even see it. You didn't even know. I just truncated it off. So you couldn't read it. But now in Infinite Campus, we can't do that. They do the rounding automatically for us. Okay, to do sine squared. If you think I wouldn't work with somebody. Yeah. Chris, question? We're not done yet, Chris. Read it.
Yes.
Only squared e of the sine. Okay, you asked that. So you need from sine as well.
Wait, Emily. Emily. Emily.
I don't.
We get it.
Yeah. I just saw it. Okay. Questions on this? Now, you guys, this parametric stuff, as long as, again, you just know what to do, like it's just very straightforward. There's not a lot of conceptual thinking of like, I don't know, you know how some of them get tough and you have to like try to interpret and all these things? This is very straightforward when you get to the parametric. These are questions that you cannot miss on the AP test.